that is 511. We are basically in the last topic that I would wish to discuss. But today I will just discuss a very specific element of that topic, and then we shall class, and maybe the subsequent classes will just be for revision purposes. Now, like I said, I've already sent out the last set of notes for your reading, so I hope you can catch up with that. I'm still not sure about your exams. We're still waiting for the university to provide guidance on that. Now, there is a question I have just come across that's very, very important. I think I will start this class by sharing that question. So please do this exercise. Go and do this exercise before I do what I expected to do today. So consider magnetically suspended ball. We've done modeling before, so this should not be a problem. As shown in the diagram below. This is just a by the way. I need you to remember that. The current through the coils induces a magnetic force which can balance the force of gravity, and cause the ball to be suspended in mid-air. So this is the diagram. We have a nice diagram here. It's a typical electromagnetic diagram. Okay, so that is the diagram. Of course, this is, let me label this is a resistor. Of course, this is an inductor. Then you've got your voltage supply there. Typically, this ball would be suspended here. So there's a height of suspension. So because basically the ball is made of a magnetic material, so it's being suspended mid-air by the fact that gravity would want the ball to fall down, but the magnetic effect or the magnetic force is holding or is countering the gravitational force. So the ball remains suspended in the air. There's another force there. Let's call it mg. So the question is, represent Let me just write it again. So the question would be model the system and so let's model the system and draw the state space representation. The state space representation. Of the system. Okay, so this is just an exercise for you to go and do. Now, basically, what I'm trying to derive to is that we have been discussing about the state space methods that we can use for controller design. We have so far actually just seen how we can model different. So we've done the modeling aspect where we look at an electrical system or electromechanical system, whichever system it is, and then we model it, see how we can represent it in terms of state space. What I want us to do today is what we call controllability and observability. Then in the last class, we are going to look at the design, so control design using pole placement. Remember, we did this with root locus, where we were placing poles and zeros at strategic locations to affect the performance of the system as per the desired expectations. So in this case also, we are done with this. I've given you another exercise to actually carry out on the modeling aspect, but I want to do this today, and then this would be for the Monday class. Then we shall call it a unit. So now, let me go straight to controllability because we only have less than an hour. So I'll start with controllability.
Excuse, sir.
Yes.
Sorry for interruption. I was requesting kindly display the question at the start, at least for just 30 seconds. There's something I haven't written.
You're recording?
Yeah, at that point.
Okay. So is that okay? This is a very simple electromechanical system. You just have to come up with the questions, then get the state variables, and then you derive the state equations and the output equation.
Yeah, done. I'm done. Thank you.
All right. So, like I've said, today I just want us to look at controllability. Let me just do them together. Then when I go to the examples, so let me do them all together at once. Now, before we go into the control design in depth, where we actually need to see where we can place poles to affect the performance of a system, I want us to look at these two principles, the principle of controllability and that of observability. So when do you say that a system is controllable? And when can you say that a system is observable? And is there a relationship between controllability and observability? We'll look at that in the next 40 or so minutes. So let's start with the controllability. Sorry. So a system is controllable if there always exists, looking for the right term, a control input if you have a control input, let's call it U of t, okay, that transfers, that control input should be able to transfer any state of the system to any other state, in finite time. So within a specified finite time, if you have a system that can take the control input, and that control input is able to transfer any state of the system to any other state, meaning the state of the system can change from one state to the other, irrespective of what the state is, then that system is said to be controllable. Now, we have linear time invariant systems. And mostly in linear time invariant systems, we can actually mathematically describe controllability or test for controllability. Okay, so in linear time invariant systems, a system is controllable. If and only if, I hope you know those mathematical expressions, if and only if its controllability matrix, will give it a symbol C, is of full rank. So when you say that a matrix is of full rank, that means if you get the rank of the controllability matrix C, you should find the value n, where n is the number of state variables. The number of state variables. In other words, n is the same order as the differential equation that describes the system completely. Okay, so for example, if you're dealing with a second order differential equation, that's a second order system, so the number of state variables would be 2. So if the controllability matrix, which I'm going to introduce shortly, is of order 2, then that system is said to be controllable. Okay, now the controllability matrix has been derived before and is described as C equals to B, AB, A squared B, and it can go on to AN minus 1B. This is the matrix. Now, please remember, we know already that A is the state matrix. We had defined all this. So I'm just reminding you, B was the input. Please mute your microphone if you're not asking a question. Please mute your microphones. All right, okay, so let's continue. So A is the state matrix, B is the input matrix. Of course, these are just definitions that we've done before while we were describing the state space representation. So you can see that this only consists of the state matrix and the input matrix. So this is the definition for a controllable matrix. So if, for example, we are dealing with a second order system, then we expect that our matrix based, and remember, n is the number of state variables. So if, for example, if the system, this is just an example, if the system is of order 2, meaning n equals to 2, then your controllability matrix would be given by, remember, you'll be having B, A, B, just like that. Okay, this is for n equals to 2. If n is equals to 3, then we'll be having C equals to B, AB, A squared B. Okay, this is for n equals to 3. And so on. If n equals to 4, we'll be having B, AB, A squared B, and then n is 4, so we'll be having A cubed B, like that. This is for n equals to 4. And it goes on and on and on, okay? So the controllability matrix changes based on the order of the differential equation that completely describes your control system. However, the test, the ultimate test as to whether a system is controllable or not is if you obtain the controllability matrix and you find that it is of full rank, meaning if you get that the order of the controllability matrix is the same as the order of the differential equation that describes the system, then that system is controllable. We'll do an example to illustrate that further, and I think you have also some of those examples in your notes. Now, how about observability? So a system is observable if the initial state, let's say the initial state of the system is x at time t equals to 0. So can be determined if you're able to determine the initial state of the system based on knowledge of the input, of the system input. And again, we'll just define the system input as u of t. And we have to do it over some finite interval, because we are not describing this system to infinity. We are only describing it over a finite time, over some finite time interval. So that means we can describe it over from the initial time when time t equals to 0 to maybe some time t is equals to, I don't know, n, okay? So for linear time invariant systems, for LTI systems, again, we have a mathematical expression that we can use to test for whether a system is observable or not. So for linear time invariant systems, we can say that a system is observable. A system is observable if and only if the observability matrix. Remember, for controllability, we had a controllability matrix C, but now we are testing for the observability. So if and only if the observability matrix, and let's denote it O, okay? Or a fancy O, okay? Again, if that observability matrix has full rank. I'll go back to that. We had said that now what that simply means that if you establish the rank of the observability matrix and it is equal to the state variables, of course, n is the number of state variables. More or less the same as we did with the controllability matrix, okay? So then we say that the system is observable. So the idea here is we have to know what the observability matrix is. Now, the observability matrix has also been established before, and it is established as C, CA, CA squared, Notice the difference with the controllability matrix. Okay, so you can see that in this case, A, we know this only consists, is the state matrix. And of course, C is the output matrix. We've done this before. So you can see that for the controllability matrix, we are only manipulating the state matrix and the input matrix to test for controllability. That is to see based on which order or which rank that the matrix is, we can tell whether a system is controllable or not. For observability, we are using the state matrix and the output matrix to obtain the observability matrix. And that matrix, again, is tested based on its rank for us to ascertain whether a system is observable or not. In the next class, when we actually do design through poll placement, we shall see the significance of controllability and observability. Today is just to know how what these principles are and how we can use them. But we are actually going to do design in the next class that would help us understand what designing an observable system means, or designing a controllable system means. Now, in other books, if you read, you'll note that controllability and observability are concepts that are dual in nature. So I can just say controllability and observability are dual concepts. You guys have been taught duality in so many areas, even in maths, okay? So for example, let me just say, for example, if you had a system, let's describe that system as AB, okay? System AB. Remember, it's a system that is described by the state matrix and the input matrix. That system is said to be controllable. I'm just trying to illustrate the duality of controllability and observability. So this system is said to be controllable if and only if a system, if you get the inverse of that system, then it becomes observable. Okay? Or if you transpose the system, then it becomes observable. So that's the duality or the dual nature of these two concepts. Usually, sorry, it's good to do examples. So I'll go to a past paper, look for questions there, because I told you I don't want to use the examples you have in your notes, because that's duplication. You can read those and understand them. So I'm only looking for an exam paper here and looking for a question on controllability. And yes, found one. Example. So let's start with controllability, because this question here is on controllability. So this question states, determine whether a system, whether the system described below is controllable. The system is described as follows. They have actually given us the state equation. -1, 2, 0, 0, -3, 1, 1, -1, -2, x plus 1, 0, 1, u. So we are to ascertain or test whether this system that has been described here is controllable. Now, well, we can, for those who might be confused, we can rewrite this system properly, because we can clearly see this is the state matrix A, the state matrix A. This is A, and this is B. Let me even use a different marker. I'm losing my voice, so I think I should stop talking soon. The state matrix A is a 3 by 3 matrix. The vector B is also a 3 by 1 matrix. But we can rewrite this system as x1, x2, x3, because we now know there's 3 state variables involved by virtue of the order of the state matrix. So we have -1, 2, 0, 0, -3, 1, 1, -1, -2. Now, this question involves a lot of matrix manipulation, and you have to be very keen with the elements, because usually you miss even a sign, then it makes everything else be incorrect. So you have to be very keen in your manipulation of these elements. Plus 101 U. Okay. So how do we test for controllability? We have just seen that generally we need to look for the controllability matrix. And the controllability matrix was given by B, AB, A squared B, and then it goes on all the way to AN minus 1B, okay? But in our case, you can see, because N here is the order of the control system, meaning the order of it's the order of the differential equation that completely describes your control system. So in this case, could actually just say that in this case, we can see clearly from the state matrix that the order is n equals to 3, because we have 3 state variables, meaning the differential equation is of order 3. So n is 3. Therefore, our controllability matrix would be B, AB, and A squared B. So it is this matrix that we have to test and see if it is of rank n, meaning of rank 3. If we test the controllability matrix C and find that it is of order 3, then we are certain that our system is controllable. Okay? So now we have to know what is B. B from our equation is 101. And this is how I would like you to solve problems like this. Okay? Don't assume I know. AB is what? AB is -1, 2, 0, 0, -3, 1. And be very careful with the elements. And if I make a mistake, please let me know. I don't have the solution to this. Multiplied by B, which is 1, 0, 1. So this is a 3 by 3 and a 3 by 1. That should give me a 3 by 1. So let me multiply out 3 by 1. Multiply the rows, that is -1. So this one is just going to be -1 because the others is 0. The next one is going to be 0, 0, 1. So this one is going to be 1. The other one is going to be 1, 0, minus, should be 1 minus 2. 1 minus 2 is -1. Okay, so that is AB. Remember, I'm trying to come up with this matrix. So I need to get A squared also. A squared. A squared is basically -1, 2, 0, 0, -3, 1, 1, -1, -2. Then I squared, meaning I multiply it by itself. okay? I multiply it by itself. If I do that, I can enter this in my system and find the solution. -1, 2, 0, 0 minus 3, 1, 1 minus 1 minus 2 squared. If you square this, you should find, please check that I don't give you wrong solutions. It's 1 minus 8, 2, 1, 8 minus 5 minus 3, 7, and 3. And so I'm looking for a squared b, which is going to be -1 minus 8, 2, 1, 8 minus 5. So this question usually is just about matrix manipulation. That's usually 90% of the test, because everything else, so if I multiply this, this is very clear. This is -1, -1 minus 2. Wait, this is -1 plus 2. This is 0. I'm going to have minus, is this -1? No, I'm making a mistake. It's 1 minus 8, 2, 1, 8 minus 5 minus 3, 7, 3. So I've made a mistake here already. Usually this is a problem. If you make a mistake, everything will be wrong. So it is 1 plus 2. So what do we get here? We get 3. Then the second one will be 1 minus 5. That is -4. The last one would be -3 plus 3. That should be 0. Okay. So now the controllability matrix itself, after doing all those funny manipulations, C would be equal to B. What is B? B is 101, 101. Okay. What is AB? AB is -1, 1, -1, -1, 1, -1. And lastly, A squared B, which is 3 minus 4, 0. That is your controllability matrix. So now you would ask yourself, how then do we determine whether the rank is 3? Of course, you can see that because the controllability matrix in itself is a 3 by 3 matrix. So definitely it is of rank 3. But we have to carry out another test and get the determinant of C. Now, if the determinant of C is non-zero, the determinant of C, so if the determinant of C is non-zero, then the system is controllable. Okay, so it is not just enough to have the system as of being rank n. In this case, n is 3, but the determinant also must be non-zero, because if the determinant is 0, then it means we cannot describe the system as controllable. So we have to obtain the determinant of C. Again, so you have to do, because it's a 3 by 3 matrix, you can do it the long way. For me, I'll type in this and get the determinant. 1 minus 1, 3. 0, 1 minus 4. 1 minus 1, 0. Okay. So you'll find that the determinant is coming to -3. You can check that later if it's true. So then you have to conclude that since since the controllability matrix C is of rank 3 and the determinant of C is non-zero, because it is -3 in this case. It is -3, it is not 0. Then the system is controllable. Then the system is controllable. So, ladies and gentlemen, this is how we test for controllability. You must know what the controllability matrix is. In general, you have to know the order of your system, the differential equation that completely describes your system. And then you have to do the matrix manipulations as indicated. Then you have to get the determinant of the controllability matrix C. If the determinant of that controllability matrix C is non-zero and the controllability matrix itself is of rank n, then you can conclude that the system is controllable. Let me look for another one, another question. This time testing for, okay. Another example. This is testing for a different thing. Determine whether the system described below is observable. So the system is given here as, remember these are vectors and matrices. So books, you will see that most books use bold letters to describe them. It's only that we can't use that here, but we understand that they are matrices and vectors. 1 minus 3 minus 1 x plus 1 or 1 u, and y is given by 1 0 minus 1 x. So here we are given another system, but in this time, this time we're supposed to test for observability rather than controllability. Now you can see clearly from the question that we have been provided with the output equation, because remember, the observability matrix, unlike the controllability matrix, the observability matrix makes use of the state matrix and the output matrix. So we need A and C, not A and B. We need A and C. That's why the output equation is provided in this case. It was not provided in the previous case for controllability. So again, here we know that the observability matrix in general, the observability matrix in general is this. Please note it was O equals to, so we had C, CA, I think it's CA squared, and then all the way to CAN minus 1. So this is the general equation for the observability matrix. Again, you have a quick look at our state equations. You can see that we have 3 state variables. We have 3 state variables because look at our state matrix. It's a 3 by 3 matrix. So we have 3 state variables. And therefore, in this case, the observability matrix equal to C, CA, and CA squared. Why? Since N equals to 3. Because we can tell from the observability matrix, we'll have x1, x2, x3. So we have 3 state variables. So that means, and remember, our state variables are usually picked from the differential equation that completely describes the system. Now, we'll have to go through the matrix manipulation all over again. Remember, we have to test again, one, if the observability matrix is of full rank, meaning its rank has to be of order 3. And then we have to get the determinant of that matrix and make sure that it is not 0. If the determinant is not 0 and the observability matrix is of full rank, then we conclude that our system is observable. Okay? So in the few minutes remaining, let's see if we can do that. Again, please check me if I'm making any mistakes. Just let me know, because these matrix manipulations can be a little tedious. So again, I need to find C. C I know is what? C is 1, 0, minus 1. 1, 0, minus 1. Like that. So I have to find CA. And CA would therefore be 1, 0, minus 1 multiplied by A. And A is given as a 3 by 3 matrix. So minus 2, it's 2, 10, 12, 131. Minus 2, and 131. Okay. So this is a 1 by 3. I think this is a 1 by 3 and a 3 by 3. So we should get a 1 by 3 actually. So we should get a 1 by 3 matrix here. So to get the 1 by 3, we'll have this multiplied here. That is minus 2, minus 2, minus 1, which is minus 2 plus 1, which is minus 2, minus 1. This is minus 3. This is minus 3. The next one would be 1 plus 3, which is 4. The next one would be, that is 0, that is 0, that is 1. This is 1. Yeah, that's easy. The next one, we need to look for CA squared. And CA squared would be C, which is 1, 0, minus 1. Then you have to multiply minus 2, 1, 0, 0, minus 1, 2, 1, minus 3, minus 1. This is squared. But you still get a 1 by 3. Yeah, you still get a 1 by 3. So let me enter this in my system to see if I can get it. Minus 2, 1, 0, 0, minus 1, 2, 1, minus 3, minus 1. Then square it. Okay, now to square it, I need a multiplication of C and A squared. I'm trying to use MATLAB to help me do this. Okay, so now I have from my solution here, you might check, is 7 minus 10 and 7. Okay, so therefore the controllability matrix O is going to be C, and C is 1, 0, minus 1. Then CA, which is minus 3, 4, and 1. And then CA squared, in my case, is going to be 7, minus 10, and 7. Again, you can clearly see that this is a 3 by 3 matrix, and so it is of full rank. However, we need to know what is the determinant of the observability matrix. The determinant of this matrix, let me just get determinant of O. That comes out to be 36. Okay, so since you always have to justify since the determinant of O, the observability matrix, equals 36. That means it is non-zero. Okay. And O is of full rank. Again, that rank is 3. Okay. Then the system is observable. So these are simply mathematical ways of testing for controllability and observability, those two concepts. Now, the information might seem abstract at this stage, why we need to test for observability and why we need to test for controllability. But when we actually do the design work in the next class, as I intend to, then we are going to see why it is important that while you're designing your system, you consider observability and controllability. So that is going to form the basis of our discussion in the next class. We are going to design control systems, but using pole placement method, and of course, making use of state space representation. And therefore, we will also consider observability and controllability. Remember, the two concepts, observability and controllability, are dual concepts. So usually, it's very easy to determine one or to test one concept from the other. Okay, so that becomes our discussion today. Unless there's a question, we have a few minutes to the end of the class. You may ask, and then we can end the class here. And then hopefully you will carry out your own studies and do the examples available in your notes. Anyone who has a question, please ask.
Excuse me, I have a question.
Yes.
For determining the determinant and the manipulation of the matrices, are we allowed to use the calculators?
Oh, yes. Okay, that's a good question. I don't intend to test whether you are able to calculate the determinant of a matrix. So you can use calculators, because what I'm testing is, one, do you know the observability matrix? Do you know the controllability matrix? Number two, can you display your manipulation of the individual elements of the observability matrix or of the controllability matrix? Meaning, can you write just the way I have indicated here? You can see that I was writing what the matrix B is, what matrix AB is, what matrix A squared is, but I don't expect you to show me how to calculate the determinant of a matrix, because you can use your calculators. That I'm not testing. It's not math. It's not a math class. I'm not testing how you determine your determinant. You can use your calculators to do that. That's fine.
Yes.
Good. Any other question, ladies and gentlemen? All right. So we'll end the class here. My voice is getting a little hoarse. So we'll meet on Monday and clear up whatever is remaining as regards the design using pole placement method. So thank you very much for listening. And I think I'll see you guys on Monday. So have a good rest of the week.